Our eyes deceive us sometimes with integrals. Here's what I mean for 16. Wasn't it like a semicircle like that? Negative 1 to 1. The problem, though, is if you find the area of the semicircle, you're not finding the integral. Right? Isn't this what you want? So you'd have to do a big rectangle minus the semicircle area. Do you see it? That's what you did?
Yeah.
So you're looking for your lunchbox?
Yeah.
It's on the front, but I wasn't sure if that was Vince's or yours, so his early dismissal's there too. Don't try to use that. Don't try to leave. All right. So what we got? 1 minus. What was the area of the big rectangle? 2. Thank you. This was the height of 1. So 2. Rectangle. 2. And then did you do the integral? How did you guys?
Subtracted area.
It said to use geometry, right? Didn't it say to use geometry for that one? So you did the area of the semicircle, which is what?
I got
1/2 pi times what's radius?
1
Squared. How'd they write the answer? 4 minus pi. That's that area. 2 minus that area. Was that right? What are we missing here? Radius is 1. Half of pi r squared. Give us that area. They had what? 4 minus pi over 4? 4 minus pi. Oh, wait. We have what? 2 minus. We have 2 minus pi over 2. That's 4 minus pi over all over 2, isn't it? Not 4 minus pi over 4. You guys agree? Common denominators, 2. That'd be 4 over 2. 4 minus pi all over 2. Is that what you guys got?
No, you have to divide it by 2 because it's over like 2 pieces for the average.
Did they ask for average value?
Yeah.
Oh, I was doing the integral. There we go. Read the directions, Mr. Westfall. The integral would be 2 minus pi over 2, or 4 minus pi all over 2. But the average value would be times 1 over b minus a, times 1 over half, right? 1 over 2 of that. I can't talk. 1 over, and then 1 minus negative 1 is 2. So 1 over 2 times that. So that's where you get your 4 minus pi all over 4. Thank you, Ashley. So those of you who also missed it, did you do the same thing I did? All right. If you're going to make a mistake, that's a good one to do, I guess. But remember, if they're asking average value, you have to do times 1 over b minus a. Any other questions? I mean, even though they're odd, did you have any trouble with any of the other questions you'd like to see worked out? Properties okay? Using the properties? Okay on this? All right. So we're going to finish up 5.3 today. let's take a look at our calendar. I updated it with the snow day. So 5-3 day 2 today. We'll review tomorrow and then quiz on Monday. I updated it on next week. So Monday. All right. So quick little visual kind of recap what we did on Tuesday. If you're talking about mean value, okay, this line right here represents the average value of the blue function. Okay, and we're going to keep reiterating this with velocity and time. Remember, there's a certain time, c, where the function takes on its average value. And it's not always halfway between the interval, right? It's not always going to be that. It's not always the symmetry that the function has. That c value could be over here, depending on the function. So if you're asked to find out where the function takes on its average value, you're going to have to set the function equal to what the average value was. Thank you.
Yeah, she talked to me for like another 4 minutes after.
All right. Next thing, we've already realized this, but you're going to want to make sure you put stars next to this. And make sure you understand that the toughest part isn't the actual execution of this problem. It's the understanding the notation of this problem. So take a look at it and see if that makes sense. All right, so let's do a visual here. And this is really something that we're going to dive into very heavily in 5-4. So I'm not going to get too far into this right now. But do we understand we're going from A to X? This is why I had you do that punchline worksheet together. Was that Monday? When did we do that? Monday? We did that worksheet together that had column 1, 2, and 3. Okay, that's so important because it's going to help you understand this better. So what do we have here? We have what's called the integrand f of t. Okay. If I just wrote this, if I wrote the integral from a to x of f of t dt, what does that represent visually on this picture? Area? The area under f of t between a and x. It's this. We don't quite know how yet, but what does that green area have to do with f of t? It's something to do with its what? Remember how they told us in that worksheet? Let this be a of x, b of x, c of x. What was that column? Column 2, what was the a of x, b of x, c of x? It was the what? You're whispering it. The antiderivative of f of t, wasn't it? Right? I don't know we don't know how to do this yet. But whatever that is, as x moves, whatever that is, that green area has to do with the antiderivative of that function. We realized that, didn't we? That's not what this is asking you to do, though. It's asking you to take the what of it, the derivative of that. Where does that bring us back to? Column 1, column 1 with x's. You see it? I can't overstate how important it is that you understand the notation here. They are going to challenge you a bunch of different ways to understand that notation. Please ask if you're confused. Does it make sense? Go ahead, Max.
I'm just confused a little bit, so.
Yeah. So if I were to walk through step by step, I would look at this and I would say, okay, that's the graph that I'm finding the area under. This tells me where to find the area from and to. And now I have this picture. Okay? This green area is represented by capital F of T.
Yeah, the anti-drift.
Yeah, and I thought we might have this problem, so I brought this up. Okay, help me out with this. This was f of t. This was f of t equals 2t plus 2. Was it 2t plus 2? So if I were to just do this, wouldn't that be this green area right there?
Yeah.
What is that? What did we get for that? C of x was?
X squared plus 2x plus c.
Yeah, and here it was what?
What's it, 1?
Plus 1. That, x squared, not a good color choice. A little thick. Third time's a charm. That's the area function in there, isn't it? Let's see if it works. What if x slides out to 5? What's the area? 5 squared plus 2 times 5 plus 1. Does it work? Yeah, because this is an area function. The area from -1 to x, -1 to 5, will give me that area. So let's contrast what's happening here, Max. I think this might help. If I stop here, this tells me to, again, this is called notational fluency. How well can you read the notation and understand what it's asking you to do, okay? This says you need to when you see a square root, you know what you're looking for. It's, what number times itself? Give me that number. When you see an integral, find the area under this function from here to here. Okay, well, it's not gonna be a number unless I have a number in for x, right? If I go from -1 to 5, it's a number. If I go from -1 to x, it's a function. Yes? What if it was -1 to p? Well, it'd be p squared plus 2p plus 1. Yes? And we realized that was x squared plus 2x plus 1. Are you with me so far?
Yeah.
Now today's lesson, we are taking that worksheet answer, okay, and we're adding a piece of notation to it. They're asking us to do the what, to take the what of that, the derivative, okay? So if I take the derivative of the left side, I have to take the derivative of the right side. Are you with me? I mean, and I'm not doing this abstractly like these notes are. This is very abstract. This applies to every possible f of t that's continuous. I am showing you exactly how this is going to work. This is what they're asking you to calculate. This is how I calculate it. What's the derivative of x squared? What's the derivative of 2x? And the derivative of 1? 0. And what do you notice this is? This is, careful, What is that? It's not f of t. It's f of x. Little f or big F?
Little left.
Little f. This was big F. They wanted us to call it big C, but it's big. It's capital F, isn't it? It's the antiderivative. What's this thing? Little f of x. Isn't that what they wanted us to realize here? You take the derivative of this antiderivative thing that gives you area, and you get back to where you started. I'm going to say it again. I need you guys to get this. Okay? We're going to build on this as we go, but you have to get this. I get this is confusing. This is the graph you're finding the area under. You're going from A to X. If I just asked you to do that part of it, it would be an area function. Plug in X, get out an area. Plug in a new X, get out a new area. Plug in another X, get an area. But that's not where we're stopping. That's a function of area. If you take the derivative of that function of area, the derivative of that function of area brings you back to where you started with x's. Oh, it's an inverse operation. I took the derivative of something and got back to where I started. That something must have been an antiderivative. Are you with me? Okay, so we have that written down. I feel like I need to show you explicitly how this works, okay? Before I do, do we know what the answer of this is going to be? Visually. The only reason I say is because we solved this one in our calculator before. Two, remember that? Where do we stop adding area? Well, isn't the sign of pi 0? Isn't this pi right here? So we're actually being asked to calculate that. I'm not sure if we're ready for this yet. I might want to show you one more thing. You have this written down? We're going to do this in just a second. And the next thing you don't have to write down. I just want to get you guys making the connection here. All right, we have our velocity data. It doesn't matter if it's a scatter plot or a curve. The area under it represents what? Your position. That's correct. I'll take that. Huh? Distance. I'll take that. Your velocities were always positive, so displacement. Yeah. Now, do you remember how all year I asked you to do S of t, V of t, A of t, and that was for a reason, okay? And that reason is where we're heading with this. Do you remember how we did F prime, F double prime? First derivative test, second derivative test. We always said if this thing is positive, this thing must be increasing, right? We went back up like that. Well, we just made a pretty important connection. The area under this thing, the area under velocity was displacement, wasn't it? In physics, how do you define displacement? If I go from A to B, how do I calculate my displacement? It's calculated as the position at blank minus the position at, what is it? Yeah, final position. You guys say final minus initial?
Yeah.
Final position minus initial position, yes? Do we all agree? This thing right here, the area under the velocity curve from A to B, gave us what when we drove? It gave us the displacement, yes? It's just, you subtracted your odometer readings. You did your final odometer reading minus your initial odometer reading. Isn't that represented by this? The position at B minus the position at A. Are you with me? How do I go from velocity to position? Because if I just need to know what the position function is and I can plug in B and A and subtract, that's pretty easy. How do I go from velocity to position? Antiderivative. Let's see if that works for this example. If I call this little f of x, let's pretend this is velocity. Okay. How do I find the antiderivative capital F of x? What's the antiderivative of sine of x? I start thinking, oh, it's cosine, right? Cosine is something. But the derivative of cosine is negative sine. So the antiderivative must be negative cosine of x. Plus some constant that we didn't know about. Every time we took an antiderivative, we had to put a plus c. Because there could have been some constant there. And here's a big point today. How can I check to make sure that's right? How do I know that's the right antiderivative? How can I confirm that's the right antiderivative of that? Take the derivative. What's the derivative of cosine? Negative sine. Oh, times the negative gives me positive sine. Right? Isn't that column 3? Didn't we check to make sure we had column 2 right? And then we took the derivative of column 3 and got back to the column 1? Right, in that worksheet? Well, if we were to, for a moment, call this velocity and this position, how do I find my displacement again? Position at I minus position at 0. Do you see where we're going with this? Do you see what I did? If I pretended this was velocity and I found the antiderivative, now we're up to position, yes? If I can find the position at pi minus the position at 0, that would be our displacement. What is capital F of pi? Well, capital F of pi is negative cosine of pi plus a constant. What's the cosine of pi? Heard it. Times a negative positive 1 plus c. Then I also need to know capital F of 0, and then I'll subtract. Well, capital F of 0 is negative cosine of 0 plus a constant. What's the cosine of 0? 1. So negative 1 plus c. So I have my position at pi. I have my position at 0. If I wanted to find my displacement, wouldn't I subtract those? So capital F of pi minus capital F of 0 would be 1 plus c minus negative 1 plus c. Am I confusing you guys, or are you with me right now? Good? Hang on? Okay. Well, let's go ahead and simplify. I have 1 plus c plus 1 minus c for a grand total of 2. What just happened here? Well, I didn't ask you to do LRAM 6. I didn't ask you to do RRAM 6. I asked you to find the exact area under the curve. And I bet you guys would agree. I bet you would agree. That process we just did was actually easier than 6 rectangles. B minus over n, plug in the left edge, left, right? 6 rectangles. What did all we have to do was do what? An antiderivative, plug in 2 numbers and subtract. That's how you find exact area under a curve. Not approximate, not rectangle, exact area under a curve. It's kind of easy, isn't it? I mean, could you imagine discovering that for the first time? Like, crazy function. How do you find the area? Oh, let's approximate. Let's do 1,000 rectangle. No, like antiderivative. Plug in this number, subtract. Done. Let's do another one. All right, now, just so you guys are on the same page with me, I'm using the analogy of velocity and position and displacement to make that connection with you, like to make sure you understand what the connection is of an antiderivative. We actually don't know that the application of this is a velocity, right? Like they're just giving us some function that we're finding the area under. I just think it helps students to visualize that as, okay, I have the velocity, I need to find the position and subtract two values to find the displacement. Because we can understand that application easier. But all you're really doing is, this is some function. All you have to do is find the antiderivative, plug in 2, minus the antiderivative at -1. That's going to give you the area. So this is equal to capital F of 2 minus capital F of -1. So how do I find the antiderivative function? Well, if little f is 3x squared minus 2, what's capital F of x? Well, what's the antiderivative of 3x squared? Add 1 to the exponent, divide by the new exponent, x to the third, minus 2x plus a constant. How can I check that? So I went up a layer to position. How can I check it? Take the derivative. See if you get where you started. Right? 3x squared minus 2. Awesome. Plug in 2. Plug in -1. Subtract. 2 cubed minus 2 times 2 plus c minus -1 cubed minus 2 times -1 plus c. 4 plus c. Look at here. -1 plus 2, yeah, 1 plus c minus -1, so double check 1 plus c, yes. -1 minus c. 4 plus c minus 1 minus c. Did you get 3? Everybody get 3? Double check my work. 8 plus minus 1 cubed. Yeah. Now visually, what does that look like? And this is a very important note we have to make here. The area from -1 to 2, and my graph might not be to scale, but do you agree it would be this? Be careful that you're going between the curve and the x-axis every time. Okay? My graph is not to scale. What is the net area? 3. What does that mean? It means its weight above the x-axis outweighs the weight below. Like when I say weight, I mean the amount of area, right? And that's what's actually happening. If I were to go from -1 to, Well, what's the x-intercept? Plus positive square root of 2/3? Whatever that is. Okay. What's happening here? My velocity, if that were a velocity graph, okay, we're calculating displacement, which direction did I start walking? My velocity is negative, 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 0. Positive, positive, positive. Yes? Here's what happened, ready? Negative velocity. I'm walking to the left. My velocity is 0 at the x-intercept. And my velocity is positive, moving to the right. Where do I end up? I don't know. How far have I been displaced from where I started? 3. That's an important distinction. I don't know where I ended up. I'd have to know where I started. What I do know, though, is wherever I started, I ended up 3 units to the right of where I started. Does that make sense? Okay. Please ask if you're confused. Any questions so far? Pretty easy way to calculate it, though, right? All right. What else do you want to do? I want to show you one more thing. Let's go back to this problem. You know how in the worksheet we did this geometrically? We did a triangle. I want to show you actually how it looks in a calculus representation. It's from -1 to x of 2t plus 2 dt. Everybody agree with that? Step 1, what do we need to do? If that's little f of t, and I'm going to use antiderivatives to solve this now. I'm not using geometry. Okay? We're actually going to use an antiderivative. What's my first step? Antiderivative, right? Which is called capital F of t. I'm going to do capital F of x minus capital F of -1. Everybody with me? What's capital F of t first? Then we'll plug in x, then we'll plug in -1. What's capital F of t? T squared plus 2t plus c. Now what? Plug in x, right? Doesn't this tell me to plug in x? Capital F of x minus capital F of -1. Plug in x. X squared plus 2x plus a constant minus -1 squared plus 2 times -1 plus a constant. X squared plus 2x plus a constant minus 1 plus 2 minus c. Good? X squared plus 2x plus 1. Which is the area function, right? You with me? Using antiderivatives. If I stopped there, it's x squared plus 2x plus 1. Everybody with me? Column 2, area function, area. Plug in x, get out an area. It's kind of nice because what if I started you guys off the integral from -1 to 3, and then I ask you -1 to 4, -1 to 5. You have to do it each time. If you go -1 to x, now you can plug in whatever x you want, right? Okay, that's kind of nice. What's the derivative now? What if I ask you the derivative of both sides? Derivative of the left, derivative of the right. 2x plus 2, back to where you started. It makes sense because that had to do with a antiderivative process, didn't it? That's how we get area. Area, antiderivatives. All right. Let's do, this is not an antiderivative problem. This is a properties of integral example. But before we do this, any questions for me? I thought there would be more of a reaction for that, honestly. Because after I spend that, they're going to be well rested. It'll be perfect. They're going to be like, wow, exact area with the antiderivatives? You're kidding me? I never thought they would be related that way. This is amazing. This is life changing. I just want to go out and calculate areas now using antiderivatives. No? Anyway, maybe tomorrow. All right, how could I rewrite this? Because I know what the integral from a to b of f of x dx is. How could I rewrite that? You guys think on that. Try it out. Once again. Talk about how much you love integral.
Bro, that house is
What the fuck are we doing? Mine said she just shut up.
A plus
She shut up. But I got into this one. I was getting into the fundamental theorem.
Well, that's the antiderivative.
So,
Right?
yeah, when the class. It was tough. And this is Brown. She sounded convinced.
Well,
I talked to you this morning, she doesn't.
Does she?
I said,
What'd you get? Confused? Would you like the geometric explanation or the calculus explanation?
yeah.
Okay. I would rewrite this as the integral from a to b of f of x dx plus the integral from a to b of 3 dx. Are you with me? Why would I break it up? Because I know what this is. I know what that part is. So I'm going to break it up because I know that is a plus 2b. You with me? Now the only thing left to find is what this is. Make me proud. 3 times b minus a. Yes, right? Constant. 3. It's a rectangle. 3 b a. Oh, what's the base? B minus a. What's the height? 3. 3 times b minus a. Which is 3b minus 3a. All right, what do we get? Negative 2a plus 5b. 2a plus 5b. See? If you want a geometric explanation, which I'm sure you wanted both, I'll just deliver. Let's say this is f of x. What happens geometrically when you add 3 to f of x? Vertical, stretch. Translation, 3 units up, yes? When you shift this up 3 units, 1, 2, 3, 1, 2, 3, it now looks like that, right? What did you just create underneath when you shifted that up 3? You created a new rectangle underneath, right? The x-axis got moved up to there. So whatever the area was, you need to add on an area of 3 times b minus a. That's a geometric explanation of it. Now you know the answers are there. We don't want to do that one today, do we? That was a trap. I wanted to see who was really still with me in Calc. There's a woman that walks by the window every day. Like right by the window. Is she there?
Yeah.
Wait, is it one of the teachers?
We should invite her. We should invite her into Calc.
Maybe she's
Miss Hager walked by next Friday. So she walks out.
Yeah, Miss
Yeah,
Hager.
she leaves. But like this woman walks against like
We just want to invite her.
when I'm retired and old, I'm gonna do stuff like that.
I
I probably get I probably get in trouble. Ooh, this is a tough one. All right, I want you guys to try this because it tests your understanding of the notation. No spoilers. No spoilers. All right, so we got x squared from 2 to k in the area of the 0. Who thinks A? Letter A. Who thinks B? Who thinks C? D. Actually, oh. Anyone want to explain what they got and why?
Because of the 0 thing.
Ah, so you're saying the integral from 2 to 2 would be 0, yes? That's reasonable. I like 2 as an answer. I hear C. Christian, why do you think it's C?
Because if you just mirror it, you go -2 to 0. Oh wait, not.
Christian answered and then argued against himself. It's impressive, honestly. Why is the integral? Why isn't the integral from 2 to -2 0? They're both positive. It would actually double that area. And by the way, what is that area? Positive, negative? Area is positive, but if you went from 2 to -2, now it would be negative, right? Are you with me? So that would be a negative area. If I went from 2 to -2, it would be whatever the area is here and here made opposite. It'd be negative, whatever that is. Are you with me? What's going on? Is he outside the door?
He looked and then
He
saw you
just
were
out.
teaching.
He looked at his watch.
Sam.
Looked at his watch.
Sam.
I'm probably in trouble. Mrs. Brown had to call me. I'm probably in
Yeah,
trouble.
he does look like a dollar bill. You're right.
All right, one more thing. I'm not gonna need to write anything down, but what was the problem I did? Sine of x dx. I went from 0 to pi, right? What if I asked you from 0 to pi, what's the average value of the sine of x function? So f of x is sine of x on the interval from 0 to pi. What if I asked you to find the average value of the function? You wouldn't just do this. You'd have to put what out front? 1 over pi out front, right?
Yeah.
So what was our answer for the regular area problem? 2. So what's the average value? 2 over pi. Do you see how to adjust that? You're still going to do the same process. You're just going to multiply by 1 over b minus a out front. Okay. pi is 3.14, so 2 over pi would be about 2/3. Meaning for sine of x, it looks like this. It goes up to a height of 1. Its average value from 0 to pi was 2 over pi, which is about 2/3, which is reasonable, right? 2/3 is reasonable. All right. We were going to do 19 through 33 before, but York had a busy night, so we didn't. So, right? Didn't you have a busy night?
Yeah.
And then even busier now because you can't.
You
Got to go to
He's left-handed.
the ER. Okay, so 19 through 33 odd on page 304. Pay attention to the directions like I didn't at the beginning of class. The tail end of the homework is going to ask you to do average value using antiderivatives, okay? One little word of warning. Can I give you guys a little bit of a warning here? Let's say you get to a problem like, I don't know, number 29, that has a 1 over x as the integrand. Ooh, do you know the antiderivative of a 1 over x? Dig deep. Dig deep. Huh? The derivative of blank is 1 over x. Natural log of x. What? Oh, I don't know. What if you come across an integrand that is 1 over 1 plus x squared? 1 over 1 plus x squared. Do I know that antiderivative? Or 1 over 1 plus u squared times d dx. Does that sound familiar? Tangent inverse? I don't know.
Literally, I'm
Why would we?